Today, we're doing something really special, resonance in the double pendulum. Now, what is resonance, right? Well, let's talk about a really simple example. If you're pushing somebody on a swing, right? If you push at just the right frequency, they'll get higher and higher and higher. But if you push at the wrong frequency, they'll kind of jiggle in the middle and they won't get resonance. So resonance is driving something at just the right frequency. So with the double pendulum, is there a frequency, right? You hang the double pendulum and you attach it to a little motor on top, and the motor will swing the double pendulum back and forth like this. The question is, does moving that motor back and forth at a certain frequency translate to the entire double pendulum moving at that frequency, right? You're not directly, pushing the bob with a certain force. You're sort of wiggling it at the top. Does the physics somehow sort of transfer that resonance from the top to the motion of the two bobs? And what do the resonance frequencies look like in the double pendulum? You're about to find out soon. Let's get started. So I had literally just finished recording this video. I go back to look at my clips and I realized I had forgot to record my screen. So here we are again for a second time, but don't worry, I'm extra prepared. So the packages today we have are, as always, NumPy, Sympy. We're doing a lot of algebraic work here, symbolic work in Sympy. We'll use SciPy for some numerical stuff, and then of course Matplotlib for making animations and plots at the end. So before I get into this problem, I want to discuss a few preliminary things which transfer over to most numerical problems. So suppose we're dealing with a classical mechanics problem and I have a Lagrangian L that looks like this. There's two masses, there's M1, and so this is the kinetic energy of the first mass, and there's M2. This should actually be an M2 here. M2, and this is the kinetic energy of the second mass. So they're the kinetic energies. And then there's also this gravitational potential energy as well, M1, M2. And now there's lots of degrees of freedom here, right? There's M1, there's M2, so there's two different masses. And there might even be other degrees of freedom in the length scale of the problem. For example, in a pendulum, there's the lengths of the pendulum arms that are degrees of freedom. So we can remove degrees of freedom by dividing this equation by certain quantities. This is common numerically. Typically, you don't deal with a quantity that has dimensions to it. You would deal with a dimensionless quantity. So what I can do is I can divide this whole equation by M1, and I'm also going to divide it by a characteristic length A for this problem. And so A, for example, could be the length of one of the pendulum arms. Now in this case, A is going to be the amplitude of the motor, but I don't have to define it yet. I'm just dividing by this characteristic length A. So now I have L divided by A squared M1. And so this is a new quantity, and if I put that on the right hand side as well, I have x1 dot divided by a squared plus y1 dot divided by a squared. I'm also dividing by m1, so you don't see an m1 here, but I have the ratio of masses here, and everything is divided by a. And you might think, this looks a lot messier. Why would I ever want to do that? Well, I can actually define a new quantity. I define m, which is equal to m2 divided by m1. So m is now a dimensionless quantity, the ratio of the masses. And I can put primes, x prime, defined as x over a. So everything with a prime is divided by a. And I get the new equation here. L divided by a squared m1 is equal to 1/2. Notice no more m1 here, but I have x1 prime dot squared, y1 prime dot squared, plus 1/2 m. So I've removed this mass here as a degree of freedom. And then I have also removed this mass here, minus g prime, y1 prime, and then this ratio of the masses as well. Now, the key thing to note here is that L divided by a squared m1 produces the same equations of motion as the regular Lagrangian L. For any constant c times L produces the same equations of motion as L. So we can solve the Lagrangian problem above, right, here. And then if we want to find x and y, for example, we just multiply by a. And we know the ratio of the masses. So this is a neat way to convert a Lagrangian problem into a dimensionless problem. Okay, so now we have the problem for the day. And the problem is we have a driven double pendulum that you can see in this diagram here. And so there's a motor, and the motor goes back and forth, and it's connected to a double pendulum. And as the motor goes back and forth, it sort of pushes the arms, and the arms, go side to side. And I define it as m1 equals 1. So I now have this dimensionless mass, right? I can choose to have m1 is equal to 1, sort of like what I have in this Lagrangian here. That's what I mean by m1 equals 1. Like this is equivalent to having m1 equals 1 here. M2 is equal to m. What that really means is that the second mass is m times larger than the first mass. And the first mass we define as unity here. Then a is the amplitude of the oscillation of the motor. But if I divide everything by a, then the motor just oscillates at cos omega t, right? So it's oscillating back and forth. There's no a. And L1 measures how many amplitudes of the motor this rod length is, and L2 is how many amplitudes of the motor this rod length is. So L1 and L2 are also dimensionless quantities in this problem because we've divided by a the amplitude of the motor. And these measure how many amplitudes the rod length is. We can solve for the coordinates, not too complicated here. We have x1 is equal to cos omega t. That's the position of the motor, right? The motor goes left and right. Plus L1 sine theta 1. Just look at that triangle here. X2 is the same thing as x1, plus it's also got that L2 sine theta 2 to go out there as well. Y1 is just, again, looking at this triangle, minus L1 cos theta 1. Y2 is Y1, and then you subtract this other thing here as well. So we have all the coordinates of the problem. So let's import the packages for today. And now we define all the required variables for Sympy. So we have T for time, M for this mass here. We have G for gravity. L1 and L2 for the two lengths here. Omega for the frequency of the motor. And we have C. C, alpha, and beta I'm reserving for later. So don't worry about this yet. But I just need those variables for some stuff later that we'll be doing. And I just define these as symbols as such. Okay, so as always in Sympy, we slowly start building up our problem. We have most of the mathematical symbols that we need, for example, like T for time, displays in LaTeX. Now I need to say that I'm defining theta 1 and theta 2, and I'm going to declare them to be functions of time. That's because they are functions of time, and when we, put it into Lagrange's equation, we'll be differentiating theta 1 and theta 2 with respect to time. So we need to make sure that we define them as functions of time in Sympy. And so we do that by running this cell here. So theta 1, theta 2 is equal to simp.symbols. I call them theta 1, theta 2. And I make sure that I have sympy.function there. And that lets them know that they're going to be a function of some variable. Then I say that theta 1 is equal to a function of time here. And so then I get the first derivative. A single d for the first derivative. Theta 1 derivative is equal to simp.diff theta 1t. So that takes the derivative of theta 1 with respect to t. And same thing for the second derivative. I take the derivative of the first derivative with respect to time, and that gives me the second derivative. And I also do all the same things for theta 2. So I can run the cell, and for example, if I want to look at theta 1, it says that it is a function of time. Theta 1d, it does indeed store d dt of theta 1 of t. So I've stored everything like that. Similarly, the second derivative of theta 2. So now I'm going to declare x1, which is a function of theta 1, y1, which is a function of theta 1 as well, if you look at this diagram here. And then x2 is a function of theta 1 and theta 2, and y2 is a function of theta 1 and theta 2. Again, we're slowly building up the problem here, right? First I said that theta 1 and theta 2 are functions of t. Now I'm saying that x1 are functions of theta 1, which itself is a function of time. So I declare these variables here. I make sure to say that they're a sympy.function class. And then I explicitly say x1 is a function of t. It's explicitly a function of t because you have a cosine of omega t here. And then it's also a function of theta 1 here. So it's a function explicitly of t and also theta 1. But theta 1 is also a function of t. And I do the same thing for y1, x2, and y2. And if I look at it, it makes a little bit more sense, right? It says x1 is explicitly a function of t. That comes in here with the cosine of omega t. Plus it's a function of theta 1, which comes in here, but theta 1 itself is also a function of time. So again, setting up the grounds here. Same thing, for example, I can look at y2. It's a function of t, theta 1, which is a function of t, and theta 2, which is a function of t. Now I can put in the specific functional form of x1, y1, x2, and y2. Now that I've declared them functions, I'm going to actually put in the variables. So I have everything that I've written above, sympy.cos omega t. It's basically just these equations written in Sympy Python notation. I define all the variables here. I can run this, and I can print them as follows. So x1, x2, right? It has everything in the right form that I want. The next thing I'm going to do is I'm going to define numerical functions for the velocities. And this is going to come in handy later in the video, right? What I'll do is I'll solve the differential equation for a specific value of a driving frequency. And if I want to get the average kinetic energy for a period of time, I drive it for 10 seconds and I get the average kinetic energy, I need to have a numerical function to get the velocities. So I have vx1 underscore f for me always means it's a numpy function, right? It's something that, it's not Sympy anymore, it's not symbolic. It's something that you give numbers and it returns a number. So for that, I have to use the Sympy lambdify function. And so, well, what function, so, right, and I'm saying that it's, this, of course, is the velocity, right? I just differentiate x1 with respect to time. And so in this lambdify function, on the right-hand side, this is the Sympy quantity. It's the thing that I want to turn into a numerical function. And then you have to ask yourself, what arguments does that take in? Well, obviously it takes in theta 1 and theta 2, right? Well, this one doesn't explicitly take in theta 1 and theta 2, but x2, for example, does take in theta 1, theta 2. It takes in L1 and L2. It takes in omega, of course, and it takes in time. And so I give it all these quantities and it will return a number just based on the Sympy expression. So I can look at vx1 underscore f, and it's a function. And if I give it a bunch of numbers, right, it takes in 1, 2, 3, 4, 5, 6, 7, 8. And if I give it 8 things here, and it will return a number, right? Some of these aren't used in theta 1, and that's fine. It just won't use those in the expression. For example, x1, vx1, which is here, doesn't have theta 2 involved with it. So even though I give it theta 2, it doesn't matter here. Okay, so now we've defined all the variables that we need. We're gonna start building up the Lagrangian for this problem symbolically. So we'll do that by defining the kinetic energy, the potential energy, and the Lagrangian. So the kinetic energy, T, is 1/2. Now remember, M1 is equal to 1. We've set it that way because we're dealing with the dimensionless problem. And then I have the Vx1 squared plus Vy1 squared, the velocities here. And then I also have the second mass. This is the mass ratio here, M. It says how many times bigger is the second mass than the first mass, M times bigger. And then I have the derivatives of the velocity for the second mass as well. My potential is V is M, remember first mass is equal to 1. G times Y1 plus M times G times Y2. And the Lagrangian is T minus V. So then I can, for example, look at my Lagrangian here. And it's somewhat of a long expression here. So it's good that we're dealing with it symbolically so that we don't have to worry about writing this out by hand. So now we're required to solve Lagrange's equations, which of course are of this form for both theta 1 and theta 2. And now it's good that we've defined theta 1 and theta 2 as functions of time explicitly in Sympy, because it's going to help us when plugging everything into this equation. So my first Lagrange's equation is we're going to differentiate L with respect to theta 1, right? If I look at L, this is L, and I can take the derivative of that with respect to theta 1, right? And that's this first part of the Lagrange's equation here. Now for the second part, I need dL d theta 1 dot, and that's this quantity here. I can also differentiate this with respect to theta 1 dot as well. And then I also have to take a time derivative outside of that. So then I have a time derivative sort of enclosing everything there. So that's equal to 0. So I have this whole thing here all equal to 0. And then I simplify it. And I do the same thing with theta 2 and theta 2 dot. And that gives me my two Lagrange's equations here for the problem. And so now I can look at, once it finishes running, I can look at the two Lagrange's equation. And what that says is that everything in these two equations, everything here is equal to 0. And everything here is equal to 0. That's how it's stored in Sympy. Now, the question is, how do we take these two equations and solve the equations of motion? Well, if I can extract everything in terms of the second derivative, for example, if I had d squared dt squared of theta 1 equals blah, then I have a second order differential equation and I can solve that on a computer. I would also need the second derivative of theta 2 equals something, and then I can solve both equations for theta 1, theta 2. It's just two second order ODEs, and I can solve that on a computer. Now it's not written in terms of the second derivatives, right? But I can extract it in terms of the second derivatives if I note something interesting about this problem. Now, looking at this problem, it's totally nonlinear, right? You have a sine of theta 1 minus theta 2. The first derivative is squared. Cos of theta 1 minus theta 2. There's not lots of non-linearity present here. But in terms of the second derivatives, right? d squared dt squared of theta 1 and d squared dt squared of theta 2, it's always linear in terms of those two factors, right? So this whole equation and this whole equation can be thought of as two linear equations that are a function of d squared dt squared theta 1 and d squared dt squared theta 2. And like the equation 4x plus 3y is 2 and 2x plus 9y is equal to 0, I have two linear equations. I can solve for the second derivative of theta 1 and the second derivative of theta 2. And then I can get two second order ODEs. And that's exactly what I do here. I say I want to solve LE1 and LE2 in terms of the two second derivatives. And it can do that because it always shows up as a linear factor of the two second derivatives. So I can get these solutions. And then, for example, this says I want to get the solution for the second derivative of theta 2. And it will print that. So this says that d squared dt squared of theta 2 is equal to this whole quantity here. And I have a second order ODE, and I can solve that on a computer. The same thing for theta 1 double dot. So I have all the information I need. I can create a NumPy function, and I can solve these equations of motion. Now, what I specifically wanted to do is I wanted to find the driving frequencies of the motor that resulted in the system being at resonance. And resonance, well, what does resonance mean? Resonance means that the two bobs are moving at the same frequency as the motor. And usually what happens then is it gets more and more and more and more energy when they're at the same frequency of the motor. And so, yes, we could solve these and get the exact solutions, but I want to solve for omega, not for the equations of motion. So we need to be clever about how we do this, and this would be very difficult to do by hand, but it's not super difficult to do with Sympy. So we're going to make a few approximations here, right? Because, we can't do this exactly. These are big equations. We need approximations. What we're going to do is we're going to assume the small angle approximation for theta 1 and theta 2. We're going to assume that the pendulum isn't moving too much, even at resonance, so that the angles remain small. We're also going to assume that theta 1 and theta 2 have solutions. Theta 1 is equal to c cos omega t, and theta 2 is c alpha cos omega t. And you might think, what the heck? Why are you choosing that solution? Well, what this says, the cos omega t says that theta 1 and theta 2 are moving in phase with the motor. They're moving at the same frequency of the motor. So cos omega t is just an oscillation, essentially. C says that, well, if it's just cos omega t, then that would be 1 radian, right? So C scales that so it's smaller. So C is just a scaling constant here. And alpha, the reason I add alpha to theta 2 is because it might be the case that theta 1 and theta 2 are moving out of phase. So if alpha is -1, then they're sort of moving opposite to each other. So I also include alpha to take into consideration the fact that they might not be the same angle both times. So there's a lot of approximations here. So if I make these approximations to theta 1 and theta 2, I can plug them into Lagrange's equation up here, and then I should be able to solve for omega. So I'll repeat that one more time. You assume solutions of this form, you plug into Lagrange's equations, you solve for omega. And there's also this other constant alpha and c, of course, that are unknowns as well. So how do we do that in Sympy, right? And there's a way to do this in Sympy. So remember, this is my first Lagrange's equation here. So what I'm going to do is first, we need to substitute things in this equation. So we need to make sure we take into account all the small angle approximations. So you'll note that I have sine of theta 1 minus theta 2 here. I should replace that with just theta 1 minus theta 2 since these are small. Remember, sine x is approximately equal to x. Cos of theta 1 minus theta 2, that's equal to 1. That's the cos x is approximately equal to 1 approximation. And I also have cos of theta 1, cos of theta 1. I need to manually go through here and see all the places where I need to make a substitution. And you'll see that there's many places here. So I do that, and I say, okay, I'm going to substitute simp dot sine of theta 1 minus theta 2 with theta 1 minus theta 2. Cosine of this with 1. So you notice I'm making all the small angle approximations here. And notice the form, of course, that this is in as well. Simp dot sine of theta 1 was theta 1. Then I'm going to put in the specific forms of these solutions, right? So theta 1 is equal to c times cos omega t. Theta 2 is c times alpha times cos omega t, right? So now I've put in these specific forms. Finally, I'm going to assume that the two lengths are the same and the two masses are the same. So for that, I set m equal to 1 so that both of the masses are unitary. And I set L2 equal to L1. And so if I just run this code here, I get the following expression. But you'll note that it hasn't actually done anything yet. It's still got these derivatives with respect to time here. So I need to make sure it actually takes those derivatives. And for that, I just call dot do it. And now it takes all those derivatives here. Now, the second thing is that we're assuming that c is small. And why is c small? Well, we're in the small angle approximation for theta 1 and theta 2. So if theta 1 is c cos omega t, then c has to be small for the angle to be small. So for now, what we're going to do is we're going to only take the linear terms in c in this equation, right? You have a Taylor expansion in terms of c in this problem. We're going to drop all higher order terms than c is 1. And for that, I add this dot series c02. And what that means is I'm only taking the constant term and the order c term. That's what this 2 here means. So I'm taking those two terms, and it creates this series. And it writes everything like this, and then it's got this plus order of c squared term. So that's some additional, it's got everything here. This is a linear in c, and a constant term here as well, plus order of c squared. And now if I don't want this thing here, I can just call this dot remove o method. And it will remove that final term here. And then finally, I call a simplify on this, and it will simplify this expression. And that's exactly what I do in this cell here, and I define it as a. Now I have this quantity a, and remember that this is the first Lagrange's equation, which is equal to 0. So everything here is equal to 0. And so I have L1, I have this thing in the middle, and I have this cos omega t. Well, if everything's equal to 0, it means that this factor in the middle must be equal to 0, right? And so I don't want the two things. I don't want this here. I don't care about this. So you'll note that there's this thing in Sympy called a.args. And it will explicitly give me, so you notice that a is equal to this times this times this. When there's multiplication factors like that, 3 terms in parentheses, like I have here, L1, this, and cos omega t. If I just type in .args, it will break it apart into those 3 terms. And I only care about the center term being equal to 0, right? If the whole thing is equal to 0, the center thing must be equal to 0. And I can say a.args1, that will give me the center argument here. And I need to solve this equal to 0. Anyways, I do the same thing for the second Lagrange's equation, doing all the same tricks I did before. And so now I have 2 equations, right? And if I look at A and I look at B, and remember, both of these are equal to 0. So I don't care about cos omega t, I don't care about L1. So for that, I type in a.args. I know the middle term is the one I care about, so a.args1. This is the equation I need to solve. For B, I go b.args. And now the second term is actually b.args2. So b.args2 is the second thing I want to solve. So these are the 2 equations I want to solve, both being equal to 0. And I plug them into this thing. I call it yeet here because I'm honestly at this point I'm running out of variable names, so I couldn't think of anything else. And I solve these 2 equations, a.args1 and b.args2, and I want to solve it for omega and alpha. So now I have yeet. And you'll note that there are 4 different solutions for yeet. 4 different pairs of omega alpha. Right? 1 is omega, 1 is alpha. For each of those 4, right? I'm solving the equation. And because there's 4 different solutions, you might think, that's sort of weird. Maybe you're expecting only 2 resonance frequencies for the double pendulum. You know, sort of both masses going like this, and also the masses sort of going out of phase, like the first harmonic of a wave equation, for example. the fundamental node and the sort of other node like this. That would be sort of what the pendulum's doing, but there's 4. So why is there 4? And the reason there's 4 is because there's also negative frequencies involved as well, right? It'll solve for negative frequencies, which we don't care about, so we only care about the positive frequencies. So for example, a yeet 3, 0, I take 0, 0 corresponds to the omega because I gave it first. That will give me a value of omega, and this is positive. Whereas yeet 2, 0 is the negative of that quantity. Now, you'll note that this is still pretty messy, and we have this unknown C here as well. So we don't know quite what the resonant frequency is. But we're going to make yet another approximation. I'm going to say, okay, let's let a new variable beta equal C times L1, and let the limit beta go to infinity. What does that mean? Well, remember, C is the amplitude of the radians of the oscillating of the pendulum arm, right? And L1 is the length of the pendulum arm. And so as beta goes to infinity, it says that the length of the arm is so big that even though the angle is small, the product of the angle and the length is large. So it says that the length of the pendulum arm is much bigger than the frequency that it's oscillating at. And that's a approximation that we can make in this case. So I say beta is equal to C times L1, and we take the limit beta goes to infinity. In order to do that, let's look at my thing here. So I have yeet, for example, 0, 0. That will give me my first frequency. And I'm going to substitute everywhere I see a C, right? I'm going to replace it by beta divided by L1, right? That's just this equation here. And then I'm going to take the limit as beta. That's this simp.limit here, goes to infinity. And so, right, if I just do this for now, I'll move this up a little bit. This is the quantity that I have. If I just substitute C as beta over L1, and now I can take the limit as beta goes to infinity, which I do with the limit here. So I take the limit as it goes to infinity, and it returns this nice simple expression. And this is the resonance frequency for the double pendulum. I can also do it for, and this is a negative frequency, by the way. We only care about the positive one. So this is the positive one, for example. And then there's another one as well. That's the negative version. And so the positive version of this frequency is equal to this. So there are 2 resonant frequencies for the double pendulum. There's the one where the 2 angle, and by the way, you can't see this yet, but I know this from the future. One of them is the pendulum going like this, and one of them is them going out of phase, and you'll see that shortly. All right, so now we're going to switch back to numerical. So remember, I had solved both Lagrange's equations completely up here, right? This, for example, is the solution. What is theta 1 double dot equal to? It's equal to this. So because I have a second order ODE, I can solve that in Python, right? That's what I have here, d squared theta dt squared. And so in order to solve a second order differential equation in Python, you need to split it up into 2 first order ODEs. And that's actually really simple to do. If you say, I'm going to let d theta dt is equal to this zeta variable here. By the way, what a beautiful looking symbol, that zeta. I've never written it on paper, I don't think, but it's cool on the computer. So I define this new variable zeta as d theta dt, and then d squared theta dt squared is d zeta dt, right? And so now you might think, oh, how do I have two first order ODEs? Well, the bottom one is an ODE of itself. That's a really simple ODE. There's 2 variables, theta and zeta, and this is one of the ODEs here. The second one, d zeta dt, is the solution here. So that's my first ODE. That's my second order E, and I have theta and zeta paired as 2 variables. Think about, if you've never seen that before, I'd recommend thinking about that a little bit. And I have these 2 equations for each of theta 1 and theta 2. So like before, I need to make numpy numerical functions here. And so for that, I take my solutions, theta 1 double dot, of course, which is this big long thing here. And I use lambdify. So my function that I want to lambdify is back here. And this takes in the variables t, m, g, omega, L1, L2, theta 1, theta 2, theta 1 dot, theta 2 dot. So it's all the variables it takes in. And I plug these in, and it will give me a number. And so that's d theta 1 dt. d theta 1 dt is simple. It takes in something, it takes in theta 1 dot, and it returns theta 1 dot. That's just these d theta dt. It returns theta 1 dot. D zeta 2 dt, same thing, and same thing with d theta 2 dt as well. So I do this for each variable, and of course I can say, well, what's d zeta 1 dt? I'll just give it a bunch of numbers here. 1, 2, 3, 4, 5, 6, 7, 8. Nope, these aren't numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it will return a number. Right? That's all it is. It's a numerical function. It says, give me a bunch of numbers and I'll tell you what d zeta dt is. And so because I have these numerical functions now, I can solve the system of ODEs. And so in Python, to solve a system of ODEs, remember we need a vector S. S is all the quantities we're interested in solving for. We're interested in solving for theta 1, zeta 1, theta 2, zeta 2. And we need to write a function that takes in S and returns ds dt. And I name it that explicitly. So it's ds dt. It takes in S. It also takes in time. And it returns ds dt. So it needs to return d theta 1 dt, d zeta 1 dt, d theta 2 dt, d zeta 2 dt. So first of all, it extracts the variables from the vector, like this. And then it returns d theta 1 dt, d zeta 1 dt, and I plug in all the variables here, d theta 2 dt, and d zeta 2 dt. So it takes an S and it returns ds dt, and it uses these numerical functions we've defined above. As you're going through this code, make sure you play around with it and make sure you understand what every step of the way that we're doing. So ds dt, again, I just give it a vector, I give it a time, and it returns me 4 numbers. That's all it does. We're just setting things up. It says give me 4 numbers, give me theta 1, theta 2, zeta 2, give me the time, and I'll return you 4 numbers. And those 4 numbers are d theta 1 dt, d zeta 1 dt, d theta 2 dt, d zeta 2 dt. And so we have the derivative written in terms of the variables. ds dt written in terms of s and t. Again, good to write your functions in this form so you understand exactly what they're doing. So now we'll plug in some numerical values to get a solution. I'll go t from 0 to 20 seconds. G is 9.81. M is equal to 1, right? The 2 masses are equal, and the 2 lengths I'll set equal to 20, because 20 needs to be much bigger than the amplitude of oscillation, which is equal to 1 in this problem. And then I'll solve it at a particular value of omega. This isn't one of the resonance frequencies. This is just a random frequency. And then we can solve it, right? If I run this cell, we can solve it. And I can plot the answer. So again, what we're doing here is we're using SciPy's ODE int function. Right, first of all, we define all our variables that we want. Then ODE int, it takes in this ds dt function. It says, you need to define for me a ds dt so that I can work. I give it initial conditions. So I'm saying that the pendulum is hanging straight. 0, 0, 0, 0 means theta 1 is 0. Zeta 1, which is equal to d theta 1 dt, is equal to 0. Same thing with theta 2 and zeta 2. So it says the initial angles are 0 and the initial angular velocity is 0, but you know the motor will start pumping and it'll start moving a little bit, and you get this solution here of theta 1 dt. The next thing I want to do is I want to write a function that computes the average kinetic energy of the pendulum. And the reason I do that is because it's useful for the resonance frequencies. If I'm at a resonant frequency and I let it move for a while, it's going to start resonating, sort of like pushing someone on a swing, and they'll have a lot of kinetic energy. If I push them at just the right rate, or if the motor is driving at just the right rate, they'll get a lot of kinetic energy throughout the period of its motion. So what this function does is it takes in a particular driving frequency of the pendulum. I say, okay, I'm going to solve for 100 seconds. I'm going to get the solution to the ODE. So I have my theta 1 and everything is a function of time. Then I compute the velocity in x1, vx2, vy2, vy1, vy2. So I have all the velocities as a function of time throughout the whole motion. And then I take the mean value of the squares of the velocities. Now, this isn't exactly the kinetic energy, of course. You have a 1/2 mv squared. But note that m is equal to 1 in this case. And in fact, I can put the 1/2 on the outside. So this is indeed the average kinetic energy for this problem because both masses are equal to 1. Again, I get my times, I solve the ODE, I get the velocities throughout the entire motion, and then I take the mean value of those velocities squared. The mean value, I sum all these squared. So it's the mean kinetic energy throughout the motion. then I do this. I say, okay, I'm going to solve the differential equation for a lot of different values of omega. And I'm going to see what values of omega give the most kinetic energy, right? And I have a theory about which values of omega will give that kinetic energy because I solved for it here. This value of omega will, and this. Oh, it's still running the other cell, so it's not going to run yet. The omega EU cell takes a little while to run, but I think it's like 1.84 root G over L that it's going to say. So anyways, here are the resonance frequencies that I said that it will gain a lot of kinetic energy at. I solved for these above. You saw me solve for them earlier in the video. So I have them here, and I predict that the average kinetic energy is going to be highest at these resonant frequencies. So let's see what happened. It truly is. Look at that. You have a peak here and a peak here. Now, they're not exact. By the way, these black dotted lines are my theorized values that I thought you would see the kinetic energy increase. So x-axis omega, y-axis is average kinetic energy. And at these values of omega, you have a high kinetic energy. And now the black lines don't coincide with the peaks exactly. And the reason for that is because, first of all, as it gains resonance, the angles are getting bigger and bigger and bigger, so you're not in the small angle approximation that I said before. The second reason is that I also made an approximation that, if you remember, C, which was the amplitude of the angle, times L was large, and this doesn't always hold either. So there were some approximations made when solving that equation, but they still did a pretty good job to tell us, approximately where these resonance frequencies are. And so I solved this for a bunch of different values, and I find that the resonant frequencies are actually pretty close to those values. And so the question is, what does the motion of the pendulum look like at those resonant frequencies? Okay, so let's actually look for the solution to the equation of motion at this peak here. What does the pendulum do? Well, we can solve the equation for 200 seconds here with all the same parameters as before. And here I'm saying I want the value of omega that corresponds to the maximum energy here. And then I plug this into my ODE solver here. And then this is a little function I use to get, first of all, x naught, y naught. These are the position of the motor. Remember, y naught is always equal to 0. And x naught is equal to cos omega t. And then I get the position of the first bob, x1, y1, and the position of the second bob, x2 and y2. And that's just a function of theta 1, theta 2, and L1, L2. That'll help me get the x and y coordinates so that I can create an animation. So I solve the answer and I get these variables here. And then finally, I can make an animation. And now in my last video about double pendulums, I know some of you weren't a big fan of my simple looking animation. So today I decided, all right, I might add a few little details myself. I'm going to add a little bit of trail here. Spoof up the animation a little bit, make it look a little nicer. So let's solve and see what this looks like. All right, so here's my beautiful animation of the single pendulum. You can see it moving back and forth, and I leave these little trails here of dust, right? And what's important is what's happening here, right? So you can see the motor is just slightly moving back and forth, and the pendulum actually comes to resonance, right? You can see that both bobs are moving together like this. But once they get high enough, then it's no longer at resonance anymore, and it loses some of that kinetic energy. Remember, with the pendulum, the period of the pendulum depends on how high up you start at. It's only for small angles that the period is constant. So if you add more and more and more resonance to the frequency, eventually the resonance frequency isn't going to match the period of the pendulum, and then you don't get that additional boost of kinetic energy here. So we're actually limited by resonance in this case. It won't sort of pump more and more and more and more energy into the system because the period changes as you get higher. So now we should look at what the other resonant frequency looks like, because it's a little bit more interesting than this. Okay, so I've modified the code here so that we look at this peak here. If you're curious how I do that, this code used to look like this. I said I used to take the value of omega that corresponded to the max value of E, and now I say I only want to consider omegas greater than 1, and so I need to make sure I add that both here and here. And so this says it's going to ignore all these values, and it will take this maximum value here. All right, so now we have the second resonance frequency, and it's exactly as I theorized. Like the string equation, the wave equation, not the string equation. I guess it works for strings too. But you have that fundamental harmonic node, and you also have that first harmonic that sort of looks like an S, right? And here you can see that the two bobs are oscillating out of phase, right? So it's almost like you have a fundamental frequency and a harmonic for the double pendulum. And now the question is there a third and is there a fourth harmonic? Well, we only found 4 solutions, and 2 of them were repeats, right? Because some of them were negative frequencies, so that doesn't really matter. But there were 2 things. There wasn't 3, there wasn't 4, like with the wave equation. Now the question is for the triple pendulum, right? The triple pendulum, you probably would see higher harmonics. Same with the 4, 5, 6, 7, 8 pendulum. And as that limit goes to infinity and you have a rope dangling down, eventually that resonance frequency will be all of the, you'll have a harmonic, you'll have a, first harmonic, a second harmonic, a third harmonic. But here, because we're connected like this, we only have a first harmonic frequency, which is like the S of the wave equation. Anyways, I hope you enjoyed this video. I had to film it twice, which was not so fun, but fun at the same time. I learned more the second time, and I hope you guys learned a bit too. So if you guys like this video, please be sure to like and subscribe. Also, check out my other videos. I have tons of numerical videos in Python for different physics problems. And I'll see you guys next time.